So, welcome, and let us begin then with a summary of the previous lecture by one of the students.
Hello, I'd like to summarize whatever you've done in the last lecture. First of all, we are discussing about certain. If you give a signal, input signal, which is periodic with time t, the output is periodic with time t. So for this, only shift invariance is a sufficient condition. Linearity is not required. So only shift invariance is necessary for this to happen. So that output is also periodic with time t. The second notion is of the Fourier transforms. So I think I'll use the board. Now, if you have a function called y, which is a convolution of x and h, then in the Fourier domain, we can say that y is a product of the respective Fourier transforms of x and h. So this also implies that this system is linear and memoryless, because it is only dependent on omega, and that's it.
All right, so let's look at the summary a little carefully. Of course, the first part of the summary was correct, that we looked at systems which obeyed the property that a periodic input gave a periodic output in the same period, and the only requirement was shift invariance. Now we also brought out the idea of a Fourier transform as a generalization of the Fourier series, right? And Amit did correctly write down expressions, except that we had decided that we require a constant to take care of the fact that the vector is a unit vector, but we had decided to put the constant on the reconstruction side, right? So although in principle this could be a pair of inverses, in most literature that is used in practice, we like to put the constant 1 by 2 pi here. And of course, a very minor point, but I must emphasize this for all students, we are normally very negligent about putting the variable of integration, and that is something that we must not forget, particularly in situations where there can be multiple variables of integration. So we must put down variables of integration. So let me correct the expressions written here, right? So here, this should have been this should have been xt is 1 by 2 pi integral x omega e raised to the power j omega t d omega, and subsequently we also looked at the role that the Fourier transform plays in the context of linear shift invariant systems. And as Amit explained, we saw that the fact that the input signal xt is convolved with the impulse response ht manifests itself in the frequency domain as the input Fourier transform being multiplied by the Fourier transform of the impulse response, right. Now, we had decided that we would prove this today formally. We had reasoned this out without proof, in the sense we showed that, this was a consequence, or this was a limiting consequence of the fact that, if you took each Fourier component, the Fourier component got multiplied by the value of h omega at the frequency of that component. So, if you take this to its limit, then each Fourier component x of omega should be multiplied by the corresponding Fourier component h of omega. That was only a reasoning that we used based on experience from the, from the context of the Fourier series. But now we should prove this result independent of its interpretation, right. So, we will start then by proving this result. So, let's first state, what are we trying to prove? We are trying to prove the following theorem, a very important theorem in the study of signals and systems. If xt and ht in fact, if xt, ht and xt convolved with ht, x convolved with ht, all have Fourier transforms. Then the Fourier transform, or the x convolved with h t has the Fourier transform capital X of omega multiplied by capital H of omega. In the language of what we did last time, right? We used this as a symbol for the Fourier transform. Now, this is a statement independent of the context in which x and h occurs. In our discussion in the previous lecture, we came to this conclusion in the context where we had an input xt to a linear shift invariant system whose impulse response was ht. But this statement is independent of the context. So, one might be convolving two signals for whatever reason, and their Fourier transforms will be multiplied in the same way. That is what we wish to prove. Now, let us prove this by essentially expanding the Fourier transform of x convolved with h. Yeah? So, how do we go about the proof? We start by expanding consider the Fourier transform of x convolved with h. What is it really? It is the Fourier transform of the following quantity. X convolved with h is this. This is x convolved with h. And its Fourier transform would be this. Is that right? Now, please note that the limits of integration are both over the entire real axis. So, wherever the limits of integration are both over the entire real axis, we decline to show them. It's understood. Where the limits are not over the entire real axis, we need to indicate. Of course, I must emphasize that we are assuming that this converges. So, that is why in the theorem we put the precondition or the axiom that x, h and x convolved with h must all have their respective Fourier transforms. That means their Fourier transforms must converge. In that case, all this holds. Yeah. Anyway, coming back to the discussion. Now we will use the same strategy. We shall put t minus lambda as a different variable. So let us put t minus lambda as a variable phi. Right? So now we try and write, this is a double integral. If you think about it, it's a double integral on lambda and on t. So we may equivalently treat it as a double integral on lambda and on phi. So now we try and write it in terms of d lambda d phi. Now it's very easy to see that, you know, the dt, so we really need to replace the integral dt. So, and what are the relations? I mean, if you look at it, we can write down the relations. I mean, lambda and phi can be written in terms of lambda and t. And one can find the Jacobian. One can find the Jacobian of, you know, this pair lambda phi with respect to the pair lambda t. The Jacobian would be 1. What is the Jacobian? The Jacobian is the modulus of the determinant of this matrix, which is 1. And therefore, the element d lambda d phi is equal to the element d lambda dt. And again, when lambda and t individually run from minus infinity to plus infinity, lambda and phi also independently run from minus infinity to plus infinity. Is that right? Going back to our understanding of double integrals, we need to rewrite the limits. So here, we may rewrite this now with this replacement by writing t minus lambda as phi, and therefore t as lambda plus phi. So all that we need to do is to write lambda plus phi and bring this here. So e raised to the power minus j omega lambda plus phi d lambda d phi. And of course, as a double integral, both the integrals run over the entire real axis. Now, if we look at this integral carefully, it is very clear that there are clearly two different integrals acting. You see, this part, I mean, this can be split as e raised to the power minus j omega lambda into e raised to the power minus j omega phi. And now we have two clear sets of terms, one that depend on lambda and the other that depend on phi. So we can first collect together the terms that depend on lambda and bring them inside. So we may write this is equal to summation, h phi outside e raised to the power minus j omega phi, and inside we shall put the terms that depend on lambda. So x lambda e raised to the power minus j omega lambda d lambda. And this whole thing is then integrated with respect to phi. Yeah? Now clearly this is the Fourier transform of x evaluated at omega. And that is independent of phi, so we can bring it outside. So this leaves us with capital X of omega multiplied by the remaining part, that's h phi e raised to the power minus j omega phi d phi. But then this is the Fourier transform of h evaluated at omega. Yeah, this is h of capital H of omega. and that proves the result. Yeah, so the result is proved. Okay. As I said, I think we should emphasize once again the interpretation of this. If in the context of LSI systems, it says that the effect of an LSI system at each frequency omega can be ascertained in a decoupled manner. That's what this says. So one can treat each frequency omega independent of other frequencies when dealing with an LSI system. That's what this says. What I must also emphasize now with this derivation or this proof is that this is independent of the context. I must emphasize this. So in general, if two signals are convolved and if both of them have a Fourier transform, then the Fourier transforms are multiplied, right? So convolution in time, which is a very complex operation, translates into a very simple operation in frequency, right? And that's the reason why, that's one of the reasons why we go from the time domain to what we call the Fourier domain or the domain of frequency. Now we should spend a couple of minutes on reflecting on what this transform has done for us and what we mean by a transform, right? What does a transform do for us? Well, I think maybe we should ask, I'd like to ask the class, what are the various things? I mean, now what I would like you to do is to look at this whole aspect of transformation, look at this whole aspect of transform from the following perspective. What does it do to the system? What does it do to the signal? Is it something, where do you place it in the hierarchy and why, right? In a sense, can you think of it as something, see, for example, I'll give you one aspect of the answer. I could think of the Fourier transform as a system. I could think of the Fourier transformer as a system in the following sense. I have a Fourier transformer here. The input to the system, if you treat it as a system, is the signal xt, and the output is the Fourier transform, x of omega. Now, this is a peculiar example of a system, because here the input variable and the output variable, the input independent variable and the output independent variable are not the same. So there are several questions which have no meaning here. For example, there is no point in asking, is the system memoryless? There is no meaning. The idea of memory or memorylessness can only be meaningful when the input and output variable are the same. Similarly, there is no sense in asking, is the system shift invariant? There is no meaning, because the output and input variables are not the same. Causality, no meaning. So these properties have no meaning now. Stability, yes, stability has a meaning. Right? And what is the meaning of stability in this context? The meaning of stability is, does this converge? So you see, you may have a bounded, xt for which this doesn't converge. Let me give you an example. Suppose xt is 1 for all t. It's a bounded input. But what is the output? You see, if xt is 1 for all, suppose xt is equal to 1 for all t. Then, what is the output of the system? The output of the system would be integral 1 e raised to the power minus j omega t dt. So, x at omega. But what is x at 0? X at 0 is integral 1 dt, which clearly diverges. So, the system is not stable in that sense, right. So, we can query whether the system is stable, and the answer is the system is not stable. In fact, that is another way of saying the Fourier transform may not exist. The system output may not exist for all inputs, right. But now we can certainly ask the question of linearity. Is the system linear? What is the opinion of the class? Yes, the system is linear. Why so? It follows from the definition of the input-output relationship, doesn't it? If we look at it, x of omega is integral xt e raised to the power minus j omega t dt. So, what we are saying is that if there is one x1 which has a Fourier transform capital X1, another x2 that has a Fourier transform capital X2, then a1 x1 plus a2 x2 would have the corresponding linear combination of Fourier transforms. That follows because you can if you simply write a1 x1 t plus a2 x2 t in place of this, then it can be split. You can just distribute that integral and clearly show that the system is linear, right. So, the system is a linear system. Or in other words, we say the Fourier transform is a linear transform in this sense. If you think of the Fourier transformer as a system, then it is linear in its input, argument or input, signal. The same holds for the inverse Fourier transform. The inverse Fourier transformer can also be thought of as a system, right. So, you may, you can write here inverse Fourier transform. The input is say y of omega, let us say, and the output is y of t. And of course, the definition relating the input and output is that y of t is 1 by 2 pi integral y omega e raised to the power j omega t d omega. So, here again it makes no sense to talk about memorylessness or shift invariance or similar or causality. It makes no sense to talk of those. But it makes sense to talk of stability and the same answer. It is not stable in the sense that there can be examples of x omega which are bounded, which lead to an unbounded output. So, it is not a stable system in that sense, right. However, it is linear for the same reasons. One can, if you have two different y's, which you put down here, the same linear if you take a linear combination of the y's, the same linear combination of the inverse Fourier transform results. So, it is not difficult to show that this inverse Fourier transform is also a linear system. So, this is a part of the answer. See, we are trying to develop this idea of what is a transform. See, I mean, from here it seems that the transform is a system. Is it a system? Is it just a system? Is there something more to it? Is there something more to it? I'd like you to reflect for a minute and tell me. What is there? The point is, we've been talking about signals, we've been talking about systems, right? Now, you could think of that process. You could think of the transform as a system. So, you could think of it as taking in an input signal and producing an output signal, if you wish to call them signals, right? You can. I mean, they're perfectly fine. But is it just that? Or does it do something more? Yes, Chaitanya. Yeah. Right. So, yeah. It changes the independent variable. Right. Any other inputs? Yes.
like we can input and output and so on, so the impulse response all are mapped to a new thing.
That's
That's 1-1 and invertible.
it's 1-1 and invertible. Okay.
To constraint like this will have jumps, major jumps, and it will be 1-1 invertible. So you can take the forward direction Fourier transformation, make whatever changes you want in the Fourier domain, and come back to your output.
All right. Any other inputs? Any other?
And also you've changed the basis around which your output.
That's right. You've changed the basis. That's right. Okay. So there are lots. Let me summarize some of the points that have been raised. If there are others, also please raise them. Let's look at. See, so Chaitanya said that there is. So just in one sentence, Chaitanya, what did you say? It alters the independent variable, right? So in one sentence, it alters the independent variable. Then there was an opinion that it is invertible, right? There's an invertibility somewhere. So let's bring in all the notions one by one. There's, so I think let's put them down also. What does a transform do? Right? So, what is a transform? Alters the independent variable. It inverts the independent variable. Why do you say it inverts? That's so alters. I think alters is more appropriate, isn't it? Well, the other thing is there is a one-to-one, right? It's the idea of one-to-one. Yeah? There was another idea brought in that, you see, the transform doesn't act. That was a very important idea which Saurabh brought in. It's not just an action on the signal or on the system. It's an action on the whole process, signal and system. So it's an action on signal and system. All right. Then, of course, other things are definitely there, in the sense that the transform could be linear or may not be linear, and so on. Those issues are separate. But this is a very important. These are very important points. The points that are brought in here. The first point, that it alters the independent variable. Now, why does it alter the? In fact, there is a link between these ideas. It alters the independent variable, and in the transform that we have discussed right now, it does it in a one-to-one manner. One-to-one manner means you can alter, and as Uday says, you can go back. Right? So it's one-to-one. Now, this is important. Now, see, the thing is, I must mention, this is always a criterion for a transform. Actually, not so. There are transforms known in signal processing where you can go back to the same independent variable, but they have their importance. This is not the case with the transforms that we shall discuss in this course, but there can be some examples of such transforms as well. An example is something called the Hilbert transform. I shan't discuss it in this course, maybe towards the later part, but the transforms that we shall discuss initially will satisfy this. One-to-one. Here again, most transforms that we deal with at the first stage do have this property. That is, the Fourier transform is an example. Later on, we'll deal with the Laplace transform. That also is an example of this under certain conditions, right? And finally, in a way, because it alters the independent variable, and in the context where it is one-to-one, it is a manifestation of a change in the way we look at both the signal and the system. That is a point that needs to be emphasized. You see, now for example here, what does the Fourier transform do from the perspective of the third point? You see, the Fourier transform takes this whole situation. You have this time domain interpretation. So you have, see, it alters the domain. So you have a time domain representation where you put in xt, convolve it. So it's an LSI system. You convolve it with ht, and it results in yt. This is convolve, right? On the other hand, in the frequency, the same thing can be viewed in a different perspective, right? One can view it in a different perspective. So one can view it as putting in x omega. Again, there is an LSI system with, now we will give it a name, we will give this quantity a name very soon. With the impulse, the Fourier transform of the impulse response given by h omega to produce y omega. And here the operation is multiply. So from convolve, the system that convolves here multiplies in that domain. So it, you know, it also, as somebody pointed out, there is also a transformation, there is also a change in the way the system behaves in the different domain. An operation of convolution translates into an operation of multiplication. We shall similarly see what happens to other operations later. For example, if you happen to shift this input, what happens to the corresponding, you know, and so on. We'll come to that interpretation later, right? But the point is, it also changes the way in which the system operates. Sometimes to convenience, sometimes not to convenience, right? So you see, it's in the context of LSI systems, it's certainly very advantageous to use the Fourier transform. And it must also be understood that sometimes it could be possible that this is invertible, in the sense that if the Fourier transform exists, there is a one-to-one correspondence. But the Fourier transform may not exist for all xt. So it might happen that only a limited class of these can be put into a one-to-one correspondence with these, right? So what I am trying to explain to you here is that, you know, in the beginning of the course, we had two levels in the hierarchy. We had signals, we had mappings from signals to signals which were systems. Now we have one step higher. We could think, of course, we could think of transforms as mapping on signals, but we could also think of them as mappings on systems or mappings on the whole signal system context. So it's one step higher in the hierarchy of our discussion, right? That's what transforms are. They're one step higher in the hierarchy of discussion, right? Signals, systems, and then transforms. But of course, transforms also pose or also behave as systems. Like the Fourier transformer can behave as a system when acting on a signal. But the Fourier transform in total can transform or change or remanifest the whole context of signal and system in a different way. We shall see that the same thing will happen with the Laplace transform later. Or we will also be studying the Z transform later. It shall also happen in the context of the Z transform. It remanifests the whole way in which we look at the signal and system context. Yeah? So now with this background or with this discussion on the philosophy or the context of a transform, let's go down to looking at the Fourier transform in greater depth. Now we've been saying all the time, if the Fourier transform exists, if the Fourier transform is defined and so on, right? And we've been postponing the discussion of, yes, Chaitanya? Does it always change the region of support? What do you mean by region of support? Okay. That's a good question. Is it necessary that the domain, the region of support is not changed? No, it's not necessary. In fact, we'll see later when we talk about discrete time systems that it actually changes the region of support. Does it always change? No, it doesn't always change. For example, in the Fourier transform, you know, the domain of support is the same. It's the real axis for time and real axis for frequency. There would be a yeah.